Today I'll be presenting my process and results for my black hole lab in Physics 2211. The objective of this lab was to analyze the motion of a star orbiting around a black hole and measuring its net force at different time intervals in order to estimate the mass of the black hole. In this lab, we'll be incorporating Newton's second law, also known as the momentum principle, stating that the net force of a system is equal to the system's change in momentum over its change in time. In this lab, we can say that the net force acting on the star is equal to the gravitational force from the black hole. Down below, we can see the magnitude of the gravitational force being equal to the gravitational constant times the mass of the first object times the mass of the second object divided by the distance between the two squared. We also solve for the parallel and perpendicular components of net force. The parallel component is a component that is in the same direction as the system's motion, which will be either causing an increase or decrease in the system's speed. The perpendicular component is perpendicular to the system's motion, which will be causing a change in direction of the system. Now, with these two components, the parallel and perpendicular components, we can add them together to find the net force of the system. And with the net force of the system being equal to the change in momentum over change in time due to Newton's second law, we can say the same for the change in momentum over change in time with its parallel and perpendicular components. Some assumptions we'll be making are that the black hole is located at the origin and that the black hole is not moving during the star's trajectory due to its much larger mass compared to the star's mass. The mass of the star is 2 times 10 to the 30th kilograms, and we'll also be assuming that the gravitational force is the only force acting on the star. For my code, I adjusted the seed line to get my specific trajectory, and I adjusted the mass of the star to be 2 times 10 to the 30th kilograms, and I adjusted the delta t to be the amount of seconds in 1 day, which is 86,400 seconds. In my code, I solve for the final and initial momentums by multiplying the star's mass to its initial and final velocities. With those values, I found delta v and delta p right here. And using delta p, I found dp dt, which was equal to delta p over delta t. And with Newton's second law, I could equate the net force to the dp dt. I also solved for the parallel component of dp dt by first finding the unit vector of the momentum, which is p hat, and I found that using the norm function on the final momentum. I then found the magnitude of dp dt, which was equal to the magnitude of the final momentum minus the magnitude of the initial momentum divided by delta t. And using these two values, I found the parallel component of dp dt, and from Newton's second law, we can equate the parallel component of net force to the parallel component of dp dt. I then found the perpendicular component of dp dt by subtracting the overall dp dt and the parallel component of dp dt. I then equated the perpendicular component of net force to the perpendicular component of dp dt from Newton's second law, and I then found the distance between the star and the black hole right here, and then I readjusted the gravitational force equation in order to get the mass of the black hole. Here we can see the trajectory of the star starting from this position here and moving in a counterclockwise motion until it ends back in the same position. GlowScript then outputted several lines of estimated black hole masses at the different time intervals, and I then found the average value of all these, which was 1.33 times 10 to the 34th kilogram, which we can say is the mass of our black hole. We can then see the values of our net force and its parallel and perpendicular components right here. Now, what's the difference between net force and its parallel and perpendicular components to the change in momentum in its parallel and perpendicular components? Although net force and change in momentum over change in time are numerically equal, along with their parallel and perpendicular components, they both represent different things and are calculated differently. Fnet is the sum of the forces acting on the system and was calculated from the gravitational force in this lab. And change in momentum over change in time is calculated from the rate of change in momentum of the system, also known as its change in speed and direction. Now, what if we switched out the current black hole with a different one with an unknown mass? Would we be able to determine the mass of the new black hole if the motion and position of the star remain unchanged? The answer is no, we would not be able to find the new mass. With the position and motion of the star being the exact same as before, it would lead to an unchanged gravitational force. Since we solved for the prior black hole's mass using the gravitational force, we would not be able to find the new black hole's mass if the values of the gravitational force were the same.